So obviously there's a shortcut for partially updating a resource as well. We'll check that out in this demo. It's going to look very familiar, so I'm going to paste it in and then we can run through it. There we go. So we first create the exact same patch request and then we call into patch async. That is the shortcut. We pass through the resource URI and a new string content object, which is initialized with the serialized patch document, the encoding we want to use, and the media type for the content type header. Application JSON patch plus JSON. Then we again ensure that the request was successful and we read out the content. Alright, let's put a breakpoint here. Let's make sure this method is executed when we start our application. And let's give this a try. We hit our breakpoint, and our movie was indeed correctly patched. The description is set to null, and the title is set to the updated title. Alright, that's already the last demo for this module. As mentioned before, I'm going to switch back to system.text.json for the rest of the modules. That's easy enough to do. We open the program class at level of the API, and we simply comment out the code again. We uncomment it in the first demo of this module. That should do it. Let's have a look at some advanced patch scenarios. Patch and the JSON patch standard allow for much more complicated scenarios as well. For example, manipulating an array. Imagine that the Movies API would also expose a movie's actors as an array. In the example you see on screen now, we're sending a patch request to a movie that will add a new actor at location 3 in the actors array. Now imagine that such an actor has a property nationality. We could then replace that by a new value by accessing the correct actor from the actors array. So it's a really powerful standard. Yet from an API point of view, implementing support for this can get pretty complicated pretty fast. Most APIs I worked on tend to allow patch requests one level deep. So even though you can create JSON patch documents for those complicated operations in the same way as we did in the demo, it's a good idea to first check with the designers of the API whether or not the scenario you're intending is supported. Let's have a look at the summary for this module. We learned that patch is the preferred method of updating resources. Modern APIs don't even necessarily allow put anymore. The body of a patch request is described by the JSON patch standard. In essence, it's a list of operations that have to be applied to the resource. You can look at that as a change set. To create such a patch document for use with HTTP client, we can use the JSON patch document and related classes. Patch can be very powerful, but also very difficult to implement from the perspective of an API. Therefore, most APIs will not support changes that go deeper than one level. So, if you're integrating with an API, it's important to check what it allows before creating patch documents. We've used the HTTP client factory in this and the previous module for HTTP client instance management. Let's check that out in some more detail in the next module. In this module, we will learn why you don't want to instantiate and dispose of HTTP client directly. And we will learn more about the HTTP client factory, which is used to work around this problem. But we'll start by covering why there's a problem with disposing HTTP client instances. Then we'll dive into HTTP client factory in detail. This is a factory used to manage instances of HTTP client and the underlying handlers, which we've used in the previous modules. We'll cover different ways of using this factory. Directly, by using named instances, and by using typed instances. Let's dive in. I previously mentioned that an HTTP client instance is intended to be reused across requests. Yet HTTP client implements iDisposable. So from that I would conclude that I need to wrap it in a using statement and don't keep it hanging around after a request has been handled. In fact, if we look at Microsoft's documentation for the iDisposable interface, we see that it states that when an object implements the iDisposable interface, we should call the object's iDisposable.dispose implementation when we are finished using it. That is automatically done by using a language construct such as the using statement in C#. Because of that, in a lot of online samples, you'll find that HTTP client instantiation is wrapped in a using statement. Even though it's counterintuitive, this is wrong. The reason for this is that when HTTP client is disposed of, the underlying socket's HTTP handler is disposed of as well. As we learned in the beginning of the course, it's this handler that is responsible for making the actual requests. By disposing of it, the underlying connection is closed as well. So when you re-instantiate HTTP client for the next request, a new socket's HTTP handler is instantiated as well, the connection has to be reopened, and so on. Not only is this slower, it can also lead to not having enough sockets available for opening new connections, as it does take a bit of time to completely close the connection and free up the socket. Let's have a look at what the effects of this are with a demo. In this demo, we will investigate the issue with disposing HTTP client instances. We're looking at the HTTP client factory samples class, which we will use for this module, just as we've used separate classes for the other modules. Let's add a new method here, test dispose HTTP client async. In this method, we want to execute 10 requests to, say, google.com. But rather than reusing the HTTP client instance, we wrap it in a using statement so it's automatically disposed of. The rest of the method is pretty straightforward. We send the request and read out the content, but we don't deserialize because we don't need the result. Let's make sure we execute this method when we run the application. So we await a call into test dispose HTTP client async in the run async method. And in our program class, we make sure that it's the HTTP client factory samples class that's registered on the container. That should do it. Let's build and run. So far for that, it seems like the requests have executed correctly. But let's have a look at the amount of sockets that are open at this moment. For that, we need a command prompt in elevated mode, so run as an admin. We execute the netstat statement here. Netstat, or Network Statistics, is a tool that is included by default in Windows. It will show us TCP network connections, amongst other things. We add -abn as parameters. With A, we ensure that all connections are listed. B ensures that we see the process holding on to the connection, if it's available. And N just means we want to see the addresses and port numbers in numerical form. Let's execute this. And let's have a look at the results. Let's start at the top. We see that there are quite a few active connections, most of which are coming from background processes that are running on my laptop. If we scroll up a bit, we find connections to google.com. 142.250.179.196 is Google's IP address. We see that these connections are still open in a time wait state. That means that nothing will be sent over those connections, but they can still receive packets from the server over them. These are the connections that we opened and closed by disposing HTTP client. When HTTP client is disposed of, the open connection remains in this state for up to 240 seconds. So that means that these sockets are not available to open other connections over, and that can lead to socket exhaustion, which we want to avoid. Alright, now let's add another test method. Let me paste that in so we can run through it. We're going to do the same thing. We're going to send 10 requests to google.com. But this time we are going to use the same HTTP client instance for all of these requests, instead of disposing of it after one request. And let's make sure we call this method. So we await a call in test reuse HTTP client async. Important before trying this, if you're following along, make sure that you wait for at least 240 seconds after the previous test to ensure that those connections aren't open anymore, so they can't interfere with the results we're going to see. Let's give this a try. The request's executed correctly. Let's open that elevated command prompt again. And let's again send a netstat-abn command. And now let's have a look. And there we go. One established connection to google.com instead of 10 in time wait status. It's in established mode because our application is still running and we didn't dispose of HTTP client and the underlying handler. This is already a lot better. Let's continue. From that demo, the solution seems obvious. Just reuse the instance by making it static, for example, and we're good to go, right? Well, not exactly. When we reuse our instance, the connection is reused until the socket is closed. For example, due to a network disruption. But that means that DNS changes, domain name system changes, are not honored. And that's a problem, as using a DNS change to switch between environments, like switching from staging to production, is a common scenario. If the change isn't honored, requests would still go to staging instead of to production. Moreover, a lot of platform as a service services in Azure internally use this. We can work around this by, you guessed it, disposing our instance and thus the underlying handler, which we don't want to do. If you go and look online for this, you might notice that there used to be a workaround which involves using a service point instance and so on, but since .NET Core 2.1, a better approach exists, using the HTTP client factory for instance management. Let's check that out